Good afternoon, attendants. It is an honor to be here today to present my research findings. My name is Feixue, and I am come from Tsinghua University. The topic of my paper is ATC, Unelastic Transmission Control, use end-to-end available bandwidth perception. I appreciate your attention and look forward to sharing insights from my research with you. Let's dive into the details of ATC. In the field of network communications, achieving effective congestion control is crucial for maintaining optimal performance and user experience. On this slide, we outline the key targets of congestion control mechanisms. First is high throughput. An effective congestion control should ensure that spire bandwidth is rapidly and efficiently grabbed to maintain high throughput. Low latency. Maintaining low latency by keeping the length of the queue short. The fairness. Implementing max-min fairness to ensure that the network resources are distributed equitably among all flows. The convergence speed is the speed at which the flow rate stabilizes. Quick convergence is essential for adapting to changes in network conditions and maintaining smooth data flow without significant delays or interruptions. Practically, ensuring that the overhead introduced by congestion control mechanisms remains acceptable. This slide presents an overview of current congestion control algorithms used in wide area networks. The first type is heuristic algorithms. These algorithms are based on network metrics such as loss, delay, and explicit congestion notification. Examples include Cubic, Vegas, and Copa, and etc. They rely on predefined rules and thresholds to adjust the data transmission rate. Another type is periodically decision. This category includes learning-based algorithms that make decisions at regular intervals. Examples are PCC and Indigo. These algorithms use learning techniques to optimize network performance dynamically. However, current congestion control has certain limitations. This slide highlights the limitation of mainstream congestion control signals in wide area networks, specifically focusing on loss and RTT. Loss and RTT work only once the collective flow rates exceed the link capacity. This indicates that the signals may not be effective until congestion has already begun to impact network performance. This underscores the need for more proactive and responsive congestion control mechanism. And this slide highlights two significant limitations of current congestion control designs. The first one is lack of fair convergence. Current congestion control considers convergence and fairness only after the available bandwidth has already been occupied, which can lead to inefficient utilization of network resources. Also, the step size for rate increase or decrease is not related to the available bandwidth, resulting in suboptimal adjustment that can either underutilize or overload the network. The second one is lack of optimal rate change. At the startup phase, the step size for rate changes is conservative, leading to slower ramp up or slower ramping up times. However, the subsequent adjustment usually become more aggressive, which may not always align with the optimal network conditions. This is illustrated by examples such as slow start and velocity parameters in PCC, like in PCC. These limitations suggest that we can still make improvements in current congestion control mechanisms. To address the limitation of current congestion control mechanisms, we propose the elastic transmission control algorithm, ETC. ETC is founded on two key design principles. The first one is pre-congestion consensus. ETC identifies a pre-congestion signal used by all senders sharing a bottleneck to reach a common estimate of the available bottleneck bandwidth. This helps in proactively managing congestion before it becomes problematic. The second one is dynamic step sizes. ETC utilizes dynamic step sizes to achieve safe, fast, and fair rate adjustment. The step sizes are related to the available bandwidth. This allows the algorithm to adaptively respond to changing the network conditions. ETC flows paces data in microburst, which is a series of consecutive transmitted packets, which is also known as packet train in works of network measurement. The pooling rate is an estimation of the network available bandwidth, which is defined as the instantaneous receptor rate of a microburst. Intuitively, the arrival interval of the packets in each microburst is always determined by the last bottleneck it passes. Therefore, with the collection of many measurement samples, flows that pass through the same last bottleneck should obtain approximately the same estimate of the available bandwidth. Our pooling rate has the following characteristics. The pooling rate is always greater than or equal to the available bandwidth, which is mainly due to the delayed ACK. The pooling rate is less than or equal to the link capacity because there are background traffic. The pooling rate is positively correlated with the link capacity. It is important to emphasize that the pooling rate focuses more on consistency rather than the measurement accuracy. One major challenge in obtaining the pooling rate is how the sender can pace data in units of microburst. The figure shows that the typical TCP behavior, ideal pacing, and the ETC pacing mode. Pacing has long been deployed in Linux and is usually dependent on system timers. The sending interval used microburst is much more precise, on the order of microseconds compared to the operating system scheduler's millisecond precision. Current high-precision pacing solutions are mainly divided into two categories, each with its own drawbacks. The hardware solutions have limited reliability. These solutions often face practical challenges in implementation and deployment. Software solutions can be categorized into two types. The timer interrupt-based ones utilizes system timers to manage pacing, which can be impriced and costly in terms of CPU usage. The gap packet-based one involves sending gap packets to control pacing, which can also introduce significant CPU overhead. These limitations highlight the need for more efficient and scalable high-precision pacing solutions in network congestion control. In our practical implementation, we found that the arrival intervals of ACKs, acknowledgments, can be utilized for more fine-grained pacing. The table on the slide shows that the process time of ACK arrivals at different bandwidths. This is 12 Mbps and this is 100 Mbps, We can observe that ACK's arrival interval is more fine-grained than the inherent millisecond level timer. Therefore, ETC senders check whether a microburst should be sent at every ACK arrival, integrating the process of piecing, evoking into the process of ACKs. This fine-grained ACK clocking mechanism allows ETC to pace transmission more accurately and responsively compared to relying solely on system timers. Next, I will introduce the rate adjustment process in ETC, starting with rate acceleration. ETC adjusts the sending rate based on the distance between the pulling rate and the current sending rate. The distance is calculated as the division of the pulling rate and the sending rate. To determine the new sending rate and promote the fairness, we choose a convex function, a log function, as shown in this slide. Our adjustment function ensures that, first, the pulling rate caps the sending rate. That is, the sending rate will never be beyond the pulling rate. Since the log function is a convex function, it guarantees that higher rates are achieved with a more conservative step. We also prove that with this function flows move toward fairness after each adjustment. This makes ETC a fair congestion control algorithm, which can rapidly grab the bandwidth. Next, let's discuss the rate deceleration process in ETC. ETC decelerates the rate when the RTT increase exceeds a threshold. The rate decrease is based on the receiving rate of this ETC, which is the average receiving rate among multiple RTTs. Theoretically, when the sum of flows rates exceeds the link capacity, if each flow sets its sending rate to its receiving rate, the queue at the bottleneck will no longer accumulate. However, due to the ACK compression and delays at the end hosts, the measured receiving rate tends to be smaller than the actual value. Therefore, each time ETC reduces the sending rate to the middle of the sending rate and the receiving rate in a stepwise. At each rate decrease, we update the estimated bandwidth delay product with the product of the new sending rate and the minimum delay. ETC then checks whether the in-flight packets have exceeded one recalculated BDP. If so, it flashes the queue of all remaining packets immediately with a smaller rate, like this. This ensures that ETC can always converge to both proper rate and minimum latency without complex parameter adjustment. We implement ETC in C++. It is developed as a user space protocol with UDP as a substrate. We use this user space implementation to test ETC in both emulated and real network paths. ETC is implemented in the form of SDK and has served as the transmission protocol on Tencent XP2P. It supports multiple platforms, including Windows, Mac OS, and Android. We compare the performance of ETC with the Linux implementation of several state-of-the-art schemes: Cubic, BBR, Vegas, PCC, Vivage, and Copa and TACK. We deploy Python in cloud servers distributed in Beijing, Shenzhen, Bombay, Sao Paulo, and Virginia. We always run flows from Beijing to other cities. We run each algorithm with both a single flow and 3 flows 30 times to check their performance under multi-flow scenarios. Our statistics demonstrate that even on short links, ETC shows 10% and 30% one-way delay improvement in one flow or three flow scenario when compared with BBR. Compared with Copa and Vivens, ETC shows more than 15% throughput advantage with almost the same one-way delay. Besides, ETC consistently maintains a low loss rate. To verify the fairness of ETC, we test the bandwidth occupation of each algorithm when starting n flows simultaneously at fixed intervals of 5 seconds. We run the fairness test in the real-world link from Beijing to Shenzhen. As the figure shows, ETC converges rapidly after the arrival of new flows, within about 2 seconds. After all of the flows arrive at 25 seconds, flows oscillate around the convergence rate, and the difference in the flows rates gradually decreases. In the whole convergence process of ETC, there is almost no sharp acceleration. It is also important that any newly deployed algorithm is friendly to existing schemes. Given that the loss-based cubic is still the current mainstream congestion control method, we tested the performance of different methods when they compete with cubic. Considering that the performance of cubic is closely related to the bottleneck buffer size, we run experiments under multiple buffer sizes, have a bandwidth delay product to 3 times of bandwidth delay product. We can observe that BBR, PCC, and TACK greatly compress the cubic flow, and PCC even obtains a 10 times higher throughput than cubic. Meanwhile, Copa show poor competitiveness under all the buffer sizes, while ETC obtains an equivalent performance when competing with cubic without damaging its performance. To test the performance of ETC in a real application, we integrate ETC in a video player to test its performance against the congestion control algorithms that are embedded in the Linux system. In this video player, all of the lost packets are recovered. The figure shows the rebuffer rate of the video flows at different bandwidths and packet loss rate. The bit rate of the video flow is fluctuating around 12 Mbps. With a 60 Mbps link, ETC maintains almost zero rebuffer rate, even if the loss rate increases. When the bandwidth is reduced to 15 Mbps, ETC starts to experience a rebuffer rate of about 2%. This confirms that ETC makes more efficient use of the bandwidth and reduces the rebuffer rate of video playback, especially in the case of limited bandwidth. To summarize, ETC exploits the instantaneous receptor rate of a microburst as the congestion signal, which can be known before congestion occurs. Exploiting the plane rate measurements, ETC calculates the optimal rate update steps, following a simple elastic principle. The further away from the plane rate, the faster the standing rate increases. This contributes to the superior behavior of ETC in throughput, delay, and fairness. Thanks for your listening.